Hello, my name is Lee, and in this work we were interested in improving the robustness of direct or intensity-based visual localization to illumination change. Unlike feature-based methods, direct visual localization relies on the photometric consistency assumption to compute the error terms to minimize and estimate the camera motion. In other words, direct methods assume that the observed brightness or color of objects in the world are constant over time and independent of viewing direction. In practice, the photometric consistency assumption is often violated due to changes in camera parameters such as gain or white balance, non-Lambertian materials, time-varying illumination, or other types of appearance change such as weather or seasonal variations. This makes direct methods prone to failure in many common robotics applications. In order to address this shortcoming, we took inspiration from recent results in image-to-image translation and trained a deep convolutional encoder-decoder network to learn a canonical appearance transformation, or CAT, that transforms images to correspond to a previously seen reference appearance. We integrated the trained model into a standard keyframe-based direct visual localization pipeline to improve its robustness to severe illumination change. Our model architecture is a 7-layer encoder-decoder network with skip connections, also referred to as a U-net. We trained the model using pairs of images captured at the same pose but under different illumination conditions, using a pixel-wise L2 loss to explicitly maximize photometric consistency. We validated our approach using 2 high-fidelity synthetic RGBD datasets. One such dataset, the ETHL dataset, consisted of multiple camera trajectories through an indoor office environment with rapidly time-varying illumination shown in the top row of videos. The bottom row shows the outputs of our trained model, which attempts to transform each new image to correspond to the static appearance shown on the left. We compared the results of computing visual odometry using both the original images and the outputs of our trained model, and found that our direct localization pipeline achieved significantly lower error rates using the transformed imagery in situations where the illumination conditions varied rapidly as the camera explored the environment. We also found that our pipeline achieved similar error rates in the canonical condition using both the original images and the transformed images. We also investigated whether the transformed images could be used in a teach-and-repeat style metric relocalization task by first creating a map in the canonical condition and then relocalizing against it in another condition. For this we used the ETHL dataset as well as the Virtual Kitty dataset, which is a partial synthetic reconstruction of the popular Kitty benchmark rendered under a variety of different illumination conditions. We compared the results of performing metric relocalization using both the original images and the outputs of our trained model, and found that our direct localization pipeline achieved significantly higher localization success rates using the transformed images. Thank you for your attention. Please note that you can find a PyTorch-based implementation of canonical appearance transformations on GitHub. We hope to see you during the interactive session to tell you more details and answer any questions.